Hello and welcome back to my second video in plotting and calibration for sensors. In the last video we talked about having a differential pressure sensor with this guy right here that's going to measure differences in pressure between 0 and 10 psi and give us a voltage out between 0 and 5 volts. We also assumed that this was a linear system, which means our equation of our line, our ideal line right here, follows y equals mx plus b, and we said that m, this slope, every time we think of slope, we think of sensitivity, is going to be 5 over 10, since this is our maximum, our full-scale output of 5, and our full-scale range of 10. Full-scale range, full-scale output. And there was this value b that we said had another special meaning to it, that this was our null. Our null. This doesn't always have to be 0 for sensors. In this sensor it is. In some sensors it is not. Now let's talk about what happens if we calibrate this sensor and we want to look at what we call null error. So we send somebody out to our factory floor to grab a sensor, and they hook the sensor up and they begin taking data. Let's draw this with dots. We'll assume it's going to be really lots of data points here, really dense data points. And we're going to make this as linear, collinear here as we can. So we're going to make this so the slopes are the same slope. So we have the same slope. I'm going to just write the equation of the line over here. We have y equals mx plus b. Our slopes are the same. These lines are parallel. So y equals, let's see, 5 over 10. That's 1/2 x. Plus, and here's the difference, this plus b, we are no longer at 0. We have some error down here. This is little e n, error null. Let's assume for a second that this is 1 volt. So we'd have y equals 1/2 x plus 1. To find that null error, we take the absolute, I'm going to come over here, we take the absolute difference between our ideal B value, B ideal, I'll just put a little I there for ideal, and our test, our B for our test value. And we're going to take the absolute difference of those two values. This means that we could have multiple tests with multiple different intercepts. So in other words, we can have, let's do another test. Let's assume we send someone out and they do another test and they end up with another line. Okay, let's try and get this as parallel as we can here. We end up with another test line that looks like this. And maybe this line has its own slope, y equals 1/2 x plus I'm just going to do it like this, maybe a -2. Maybe we have something like that. We would still use the same thing for finding the error. There is one trick, however. When we do this, we're usually only interested in one error value, and that is the error value that has the biggest difference, the biggest absolute difference between our intended line, our ideal line, and our test line. So we're looking for the line that is furthest away in B between these two values in order to compute this error. So in this case, regardless of what the drawing might look like, my error null, my null error, would be, let's see, what is it for our real? Well, it starts at 0, 0. So for my ideal, it would be 0 minus, and then I have a -2 over here. That's the biggest absolute difference, -2. Biggest absolute difference, which means my error null, my raw error null, would be 2. And we're going to do this in our output here, 2 volts. So my null error happens to be 2 volts. Sometimes you will see this expressed as a percentage of our full-scale output. And this is a really nice, convenient way of writing things. So what we will occasionally do is we will occasionally have our error null at FSO. It'll look something like this. And what we do is we take that absolute error, that absolute null error that we calculated over there, we divide it by our full scale output, and we multiply by 100. So in this case, we have our error here of 2 volts, divided by our full scale output of 5 volts, and we would multiply that result by 100, and this is expressed as a percentage. And that's it. That's all there is to determining null error in one